Welcome back. We're still in section 5.1, and in this video we are going to be continuing our discussion of sequences, but we're now going to take a look at the idea of the limit of a sequence. And what we are particularly interested in is whether or not a sequence converges to a particular value as the number of terms approaches infinity. So we want to know, basically, do those terms approach, does the sequence approach a particular value? And one easy way to kind of see this is with a graph. So basically you can just plot those terms on an XY plane and see if those points are approaching some value. So for example, example 3, it says consider the following sequences and their different behaviors as n approaches infinity. So this first sequence that we see here is actually what we call a geometric sequence. We're adding a specific amount, in this case 3, to the term as n for every term. So the terms get bigger by 3 each time, and you can see that here in the graph. So we have 4, and then 7, and 10, and 13, and 16. And notice those terms are not approaching some specific y value. They just keep getting larger and larger and larger. So what we can say here in this case is that the sequence 1 plus 3n approaches infinity as n approaches infinity. So as n gets bigger, the terms of the sequence get infinitely bigger as well. All right, let's look at the next one. So the next one, it says 1 minus 1/2 to the n power. Well, in this case, the terms of the sequence, it starts as 1/2, and then it goes to 3/4, and then 7/8, and 15/16. It looks like these terms in the sequence are getting closer and closer to 1. So, if we wrote out the terms again, this is 1/2, 3/4, 7/8, 15/16. You can see those terms are approaching 1 as n approaches infinity. Okay, the next one, C, is a little bit different. You'll notice in this one, the terms alternate. So the first term, when n equals 1, is going to give you -1, and then you get +1, and -1, and +1, and -1, and so on. So it jumps back and forth. Terms alternate back and forth between -1 and +1. So this particular sequence does not approach or does not converge on a particular value. The terms, let's write it out, what we just said. Terms alternate back and forth between -1 and +1 as n approaches infinity. So we can say the sequence diverges, since it doesn't converge on a single value. You can see that in the graph, those dots hop back and forth. Okay, and the last one, although it does alternate back and forth between positive and -1, or positive values and negative values. So in this case, let's write out those terms. So we have -1, +1/2, -1/3, +1/4, -1/5, ... So even though they alternate back and forth between negative and positive, their values are getting closer and closer to a particular y value. So what value is this sequence approaching? What does it look like it's approaching? Hopefully, what you said is it looks like they are approaching 0. So we could say -1 the n over n appears to be approaching 0 as n approaches infinity. All right, very good. So that's kind of the idea of looking at the limit of a sequence and whether or not it converges. So parts A, B, and D look like they do converge, okay? So let's go ahead and now give a formal definition for the limit of a sequence. So given a sequence A sub n, if the terms A of n become arbitrarily close to a finite number L as n becomes sufficiently large, so as that's just saying as n approaches infinity, we say that A sub n is a convergent sequence, and L is the limit of that sequence. All right, so that's why D is a convergent sequence, because the terms of the sequence approach a finite number 0 as n gets large, as n approaches infinity. And then there's also another little theorem here that's kind of nice. It says that if we take a sequence A sub n and we treat that formula in the sequence as a function, and we are able to take the limit of that function and we get some value L, then of course that says that that function, the limit of that function exists. Well, if the limit of that function exists, then that also means that the limit of the sequence exists. And so the sequence converges. A sub n converges. And so, you know, this can be used in a lot of different ways. One thing we could use this formula for is to show some true statements about the geometric series. Different values that R sub n, that's the geometric series, that R sub n converges to based on what the value of R is. So if R is between 0 and 1, then R sub n is going to approach 0. If R equals 1, then R sub n approaches 1. And then if R is greater than 1, the geometric series R sub n diverges. We could also use some of the algebraic limit laws. We're not going to use those a whole lot. A couple more theorems. There's the squeeze theorem. And then I particularly like this one. This can be useful sometimes. It says if we take the limit of the absolute value of the sequence and you get 0, then the limit of the sequence itself will be 0. In other words, if the absolute value of the terms approach 0, then the terms themselves will approach 0. One that could have been useful on would have been this D here, right? So these are alternating positive and negative back and forth, but the terms themselves, forgetting about the signs, are approaching 0. So that's kind of a useful way. We can use theorem 5.4a for that. So let's look at some examples and see how we can apply some of the theorems we just talked about in finding the limit of a sequence. Example 4. So part A gives us a sequence, and the sequence is 3n squared minus 1 over 10n plus 5n squared. And we want to find the limit. So what we're going to use to our advantage is we're going to go back and we're going to use this theorem 5.1. Remember, theorem 5.1 says is we can take our sequence and we can represent it as a function and just take the limit of that function. And if we can find the limit of that function, then that means that the sequence converges to some value, to the same value L. So we can do that here. In other words, what we can do is we can let f of n be the function 3n squared minus 1 over 10n plus 5n squared. And then what we can do is we can take the limit of that function. So we can take the limit of 3n squared minus 1 over 10n plus 5n squared. And it may have been a while since you've done limits. This is a Calc 1 thing, but one of the things we can see here is that it looks like both the numerator, as n approaches infinity, the numerator is going to go to infinity and the denominator is going to go to infinity. So what rule can we use when we have a limit that goes to infinity over infinity? And hopefully you said L'Hopital's rule. Yes, anytime your limit gives you the limit of a rational expression gives you infinity over infinity, or 0 over 0 for that matter, we can use L'Hopital's rule. And so if you'll recall, L'Hopital's rule says that you just take the derivative of the numerator and denominator separately and apply the limit again. So the derivative of the numerator is 6n, and on the bottom we have 10 plus 10n. Okay, and so after we do that, again, you'll notice you get infinity on the top and infinity on the bottom, so we need to apply L'Hopital's rule one last time. When we do that, we're still taking the limit, but the numerator now becomes 6, and the denominator becomes 10, and 6 over 10 reduces to 3 over 5, and so this is our L. We got some finite value that function approaches, which means what? What can we say about our sequence? We can say, so that particular sequence, 3n squared minus 1 over 10n plus 5n squared, what can we say about that sequence? That sequence converges by the theorem we were just talking about, by theorem 5.1. Because we showed the function approach some finite value, that means the actual sequence itself converges. All right, so we have another one here, example B. We can do a similar sort of thing. We can let f of n equal e to the 2n over n, and then take the limit as n approaches infinity of e to the 2n over n. And again, we get infinity over infinity, so we can apply L'Hopital's rule. We have the limit as n approaches infinity. The derivative of e to the 2n is 2 times e to the 2n. We got a little chain rule there, and on the bottom we have 1. Now we no longer have infinity over infinity. We have infinity in the numerator, so this becomes basically infinity over 1, which is infinity. So what can we say about the sequence in this case? Does the sequence converge or diverge? Yeah, it diverges. So e to the 2n over n diverges by theorem 5.1. Okay, now example C is one of these alternating ones again. Why do we know it's alternating? Well, hopefully notice that it has the negative 1 to a power, which that's what's going to cause it to alternate back and forth between positive and negative terms. The terms of this sequence alternate, and so which theorem do we want to use? If we scroll back up, remember that's going to be useful, and it's going to be useful to use theorem 5.4. This is good for alternating sequences. So in this case, the absolute value of a sub n is going to be 1 over n. And so if we take the limit of that, if we take the limit as n approaches infinity of the absolute value of a sub n, it's like taking the limit of 1 over n, which in this case is going to be 1 over infinity, which is going to be 0. And so does that, again, go back to that theorem. It says if that limit of the absolute value of terms approaches 0, then the limit of the actual sequence itself is 0. So we can say, so by theorem 5.4a, the sequence negative 1 to the n over n approaches 0. So does it converge? Yeah. So -1 to the n over n converges. All right, so there we saw some examples of how we could actually find limits without having to look at the graph. There is one more example here. This is that example of an alternating sequence that doesn't approach some value, right? These terms go from +1 to -1 to +1 to -1 and so on. What do you think we would say about that sequence? Yeah, we would say it diverges. So -1 to the n diverges because the limit as n approaches infinity of -1 to the n doesn't exist, right? Those terms alternating back and forth. We're not approaching some finite value. We're approaching a set of values that swing back and forth, +1, -1, +1, -1. So again, summarizing the section, in order for the limit of a sequence to exist, the terms must approach some finite value. If it doesn't do that, then it doesn't converge, it diverges. All right, so that's going to do it for this video. Thank you. We'll see you in the next video.